Alright, welcome to the last page of the first section of chapter 14. And here we're just going to sketch both the contour map and a graph of the function and compare them. So because I'm asking you to graph these, they're not going to have to be 100% perfect. We just have to get, an idea of what the contour map would look like and what the shape of the graph would look like. So the first part we're going to do is we're going to do the contour map. So if I'm doing a contour map, I'm going to set my function f of xy is going to be k. I'm going to set that equal to the square root of 36 minus 9x squared minus 4y squared. And then I'm going to put this into a shape that I know, or a surface kind of that I know. So I'm going to square both sides. And I'm going to get k squared is equal to 36 minus 9x squared minus 4y squared. And I'm going to put my x's and y's on the same side. So what I'm going to have is 9x squared plus 4y squared is equal to, I can say negative k squared plus 36 or 36 minus k squared. All right. And now this is going to have to be for k is greater than or equal to 0. So here, hopefully you see that we have a family of ellipses with the major axis, the y-axis, or what we can say is k is equal to 6 is the origin. All right, so to draw the contour map, again, we're going to have a bunch of ellipses. And we're going to start off with, our first value. And let me change the colors. So our first ellipse is where k is equal to 6. All right, because if k is 6, we get 36 minus 30. Right here we get 36 minus 36. That gives us 0. So far, that means that our first ellipses is just going to be that dot right there. All right. Now, our second ellipses is going to be where it's 5. And then if it's 5, we plug k in for 5. We get 5 squared, so it's 36 minus 25. And so our ellipse for when k is 5 is a little bit big. Whoa. Is just a little bit bigger. All right. I'm not drawing my ellipses that great. All right, so that's 5. All right. Then if we do 4, we get a little bit bigger. Let me go ahead and create some space in there. Our next one's going to be a little bit bigger. And again, I don't have perfect ellipses, so that's 3. And then, we're going to get a little bit bigger. 2. And then, they're going to get a little bit closer together because it's not going to be as great, the distance. So 1 and then 0. It's basically going to be right there at 1. So there's the contour map of our function. And then we want to look at the graph of that. Well, if we look at the graph of it, what we're going to do is instead of saying f of xy is equal to k, we're going to set that equal to z. So we're to 36 minus 9x squared minus 4y squared. Going to solve. So we're going to square both sides. 36 minus 9x squared minus 4y squared. And we're going to, again, put this into a shape that we know. So 9x squared minus plus 4y squared, and then plus z squared is equal to 36. And so if we are visualizing what our k was, which was, quite a few, like 6, we had 6 ellipses, then what we're going to do is our contour map is going to be going up on the horizontal z. So it's going to look something like this. Let me change that to black. Try to get, that's good enough. All right. And so when we draw this out, our first ellipse is going to be, okay, that's 6. Then we're going to have an ellipse Alright, and then our ellipse is going to get bigger. And then it's going to get bigger. And then it's going to get a little bit bigger. And then this is not the best drawings. And so this is what we have. That is our surface. Alright. The last part is functions of 3 or more variables. So if we have a function of 3 variables, so we have 3 independent variables, f is a rule that assigns to each order triple x, y, z in the domain of the 3-dimension. So the domain is going to be the 3-dimensional coordinate system, and a unique real number denoted by f of x, y, z. And so a lot of times what we'll say is then the independent variable could be w, or the independent variable could be t. Because if we're having 3 independent variables, then what we have is we have a pretty much we're in the 4-dimensional coordinate system, and it's hard to imagine things in 4 dimensions. And so a lot of people, instead of denoting that dependent variable as w, some would say that time is the 4th dimension, and so that's why they use the variable t if we ever do things in 4 dimensions. Again, we're never going to graph anything in 4 dimensions. We could graph the domain, because that's, if we graph the domain of this function of 3 independent variables, then the graph of the domain is going to be on the 3-dimensional coordinate system. All right. But then the actual, thing that we get from 4 dimensions, we're not going to be able to graph.